Hi class, today we are going to be talking about harmonic motion. This is chapter 5.1, linear models that contain initial values. So let's get started. Today we're going to use a lot of the methods that we have been learning from chapter 4, mostly solving equations that are homogeneous and non-homogeneous using constant coefficients. Okay. So today we're going to start off with simple harmonic motion, otherwise known as free undamped motion. So basically what we're doing is we are going to be taking a very specific sort of model, mass on a spring, and we're going to increase the complexity of our model so that more accurately represents a lot of the things that we tend to do with mass on a spring. Okay, so the mass on a spring problem is a very, very common problem that's used in mathematics. You learn about it a lot in physics. You talk about it a little bit in pre-calculus with Hooke's law. I studied mass on a spring for a very, very long time throughout my career in applied mathematics. So it's something that is not just kind of stuck to this class only, right? So as you progress in mathematics or physics or engineering, you'll talk about this stuff. It's very, very important. It has lots of implications to real-world systems, okay? So the most simple one that we're going to talk about is mass on a spring. So for our cases today, we're going to consider a mass that is hanging on a vertical spring, okay? So when I studied this in college, most of the time I looked at a horizontal system, okay? And so you can talk about this horizontally as well, but however today we're going to talk about it vertically. A lot of times you start to talk about several masses connected by several springs connected together, and we like to model those as well, right? So today we're going to keep it fairly simple. We're going to have one spring, one mass. I think there's one or two problems in the textbook where you have two springs connected to the same mass, but that's not too much more difficult than what we're going to study today. So again, let's say that we have a spring that's hanging vertically, okay? Now this spring is going to have some sort of a compressed length, and once you put a mass on the spring, it will stretch the spring some distance, okay, and then once it stretches it a certain distance, it'll come to rest, okay, and we call that point the equilibrium point. So let's kind of go through some of the text that we have written here, right? So if you put the mass on a spring, it's going to stretch downward due to gravity, so we're going to call this the positive direction. So down for us is a positive direction in this case, okay? So the spring will resist this downward pull and will come to rest at some position which we call the equilibrium position. So again, we have a compressed length of our spring. We put some mass of mass M onto our spring, and then that mass will pull our spring downwards a certain distance and it will come to rest, okay? So again, mass and gravity are acting downwards on the spring. The spring itself has an inherent property called the spring constant, which will act in the opposite direction, pulling upwards, and the spring force and the force due to gravity with the mass will sort of equal out and bring us to an equilibrium point that we call the equilibrium position, okay? So we're going to kind of flesh that out a little bit better as we go through this video, right? But I'm just kind of giving you a preview of kind of what it is that we're going to be talking about, okay? So we're going to call the stretched position a length of S, right? So we have the compressed length, and once we add the mass on, the spring will extend a certain distance. The distance that it extends is called S, okay? That's the length that we extend our spring due to the mass, okay? So let's think about this resistance as a vector, right? Because the force due to gravity pushing downwards is also a vector. So we have an equal vector moving up, which is due to the spring constant, and this distance that it gets stretched. and that should be equal to the vector that's pushing downward due to gravity and the mass, right? So again, remember that force is mass times acceleration. So in this case, we're talking about the force due to the stretching of our spring by the mass times the acceleration due to gravity. Okay, so let's talk about our functions that we're going to use to create this differential equation and that we're trying to solve for. So our function x of t is based on time. It is the position of our mass as it relates to the equilibrium position, not to the standard position of the compressed spring, but to the position after the mass has been attached and it has come to rest in equilibrium. Okay, so this is as time goes on, as we start to put our mass spring system into motion, at what time can we expect to find our mass in relation to kind of the balance point, right? X naught is not the position of the mass in equilibrium. It is the position of the mass once we put it into motion. Okay, so if our equilibrium is here and I stretch it down to here before I let it go, this distance from, this is what I would call 0, right? The distance I stretch it, that is my x naught position. Okay, so it's the distance that I'm pulling or compressing my mass in relation to the equilibrium point, not the compression point of our spring when there's no mass attached. This is once we attach the mass and it's in equilibrium, and then we start to put things into motion. Okay, so obviously we're going to need some derivatives here. So if this is position, the first derivative is velocity. Okay, so it's going to be how fast our mass is moving at some time of t. Okay, and the initial value for our velocity, which is the same as the initial velocity here, right, input wise, the value that we get out once we plug this in is going to be the initial value, the initial velocity that we put into our system. Okay, so let's talk about this. If I pull my spring mass system down and I stop and I let it go, my initial velocity into the system is 0. I'm not adding anything into the system. Now, if I am to pull the spring and let it go as I'm pulling it in a downward direction. I'm giving it some sort of velocity as I let it go. An equivalent statement to that would be like, let's say I have it in equilibrium and then I push my system, my mass spring system up in order to get it going, right? So I put some initial velocity into it to get the spring system to start oscillating, right? So that's what we mean by the initial velocity of the system. Okay. So now let's talk about this resistant force of the spring, right? So this is the inherent force inside of the spring that brings the system to equilibrium. So again, my stretching factor here, my stretching force, is mass times acceleration, and again that acceleration is the acceleration due to gravity, right? So when my mass spring system comes to rest, it comes to rest at some equilibrium point, and that's when the mass and the force of gravity is equal to the resistant force of the spring itself. Okay, so that resistant force of the spring, we call it the spring constant. That spring constant is labeled as K. Okay, so this is basically the interpretation that we have of Hooke's law. So again, if you've done physics before, or if you remember your pre-calculus courses, generally when we do proportionality, right? When we talk about proportionality, we generally bring up Hooke's law. Okay, so it should make sense that the more I pull the spring down with the mass attached to it, the more I pull my spring down, the more resistance I feel from the spring, right? Similarly, the more I compress the spring, the more I feel it wanting to push me back away, right? So the distance, the resistant force of the spring is equal to we have a negative k here because, again, it's moving opposite of the direction of gravity. So remember, downwards is our positive direction, upwards is our negative direction. So the force coming from the spring, the resistant force, moves upward. And this is equal to the spring constant times how much we get stretched due to putting the mass on the spring and having it come to equilibrium. Okay. So again, remember, these two forces act against each other, and in order to become into equilibrium, these two things have to cancel each other out and equal zero. Or another way of saying that is that they are equal to each other. Okay. So the mass times acceleration due to gravity moving down is going to be equal to the force that I'm putting into from the spring constant times, how much the spring gets stretched moving upwards, right? So this is in equilibrium. This is when we're not moving. Now, when we are moving, when we are in motion, my acceleration is no longer the acceleration due to gravity, but due to the movement already of the spring, right? I can be accelerating upwards, I can be accelerating downwards. It really depends on my velocity, my initial velocity, all of these kinds of things. So here, instead of mass times gravity, we have our variable function for acceleration, which is the second derivative of position. Okay, and instead of having s, which is where I am when these two things are equal, it's going to be equal to whatever position I'm at when I'm at that equivalent acceleration portion. Okay, so the acceleration at this point and the distance that I am from equilibrium, those two things will be equal. So all I'm doing is changing my static value to my dynamic value, right? So this gives me a differential equation. I have x double prime, right? And I have my x function. In this case, they are changing over time. So this is my differential equation, right? Now, one thing I want to say is that for our textbook or any other textbook, this constant term here is called omega squared. We'll talk about later why that's important, but in this video, I'm going to keep everything as k over m. So again, remember, k is your spring constant, m is the mass of the weight that you are putting on to the spring. So we'll keep this as km. Your book, the internet, anywhere else, they're going to call this omega squared. Okay, omega squared. So again, for simplicity, for our derivations, so you can use useful formulas so that you don't have to think about, okay, omega is k over m, so then, or omega squared is k over m, so that means that omega is square root k over m, and then I'm going to use things here and there and there, and then these are going to change in this way and that way. We're just going to keep things in terms of the things we've been talking about that are important, which are k, s, and m. Okay, everything that we do will be k, s, and m. If you want to write the equivalent forms of the omega squares and the other things that we have, you are free to do that. Your book already does that. So hopefully you guys have looked at the book a little bit during this time that I've been, these 36 hours that I've been using to create your video. All right. So, let's talk about solving this equation. Okay. So now let's talk about when we have some examples. You can create this problem from scratch every time, or what we're going to do is we're going to solve this for every time we have simple, undamped, free harmonic motion, and we can just kind of plug our stuff in. That's really the goal for these videos, right? So if I want to make an auxiliary equation, notice I'm not using m. Okay, if I did the m squared plus km over m, I'm very certain that a lot of you, your first instinct will be, well, hey, look, I can cancel some things out, right? And I don't want you to do that. I don't want you to confuse this m squared that would be here with this m for mass that's here. So we're just going to use a different variable just to keep things from getting confusing. This r is just a random variable I use. I'm using r instead of m for the auxiliary equation so we don't mix variables up. Okay. So now what I want to do is I want to solve for r. So to solve for r, very simple. I subtract this on both sides, take the square root. That will give me an imaginary solution. Okay. So notice that the square root here of k over m is what omega would be, right? Omega squared is this, so then regular omega would be the square root of this. So I would say r is plus or minus I omega, right? So again, everyone else uses omega here just to keep things simple, but I'm going to try to keep them simple, not for the derivation, but for solving for us, right? So I'm going to keep them again in terms of Km. So since these are imaginary solutions, there's no real part. That means there's no e to the real part in my solution. It was only the imaginary portion of the complex number, so it's only cosine and sine, where the imaginary part is multiplied inside of my trig functions. Okay, so again, this is what my function solutions will look like. Okay, so note that my solutions are oscillatory, right? They're periodic functions, and this should make sense because we're going to have a mass that bounces up and down about some equilibrium point. Okay, so what does that? What oscillates? Trig functions oscillate. Okay, mostly cosine and sine, right? Cosecant, secant, tangent, they don't really do this kind of thing. Sine and cosine, they're wave functions, right? They work in a wave. Basically, I can model this oscillation about an equilibrium point with a wave, right? So it should make sense that we get a sine and cosine sort of functions. Okay, so just review our trig functions a little bit. Remember that trig functions look like this: a sine, some constant times t, sometimes added another angle here, which we would call phi, which we'll talk about later, right? A phase shift form. So, but this is our standard form for a trig function. Okay, for sine and cosine periodic functions. So this could be cosine as well. I had to choose one, so I chose sine. So remember, a is my amplitude, and b tells me what my period of my system is going to be, right? And then from the period, I can find my frequency. So a is the amplitude, b tells us my period, the period tells us the frequency. Right, so for this case, my period is always 2 pi over the value that's being multiplied times my variable, and the frequency is the reciprocal of the period. So you just flip the fraction around. If this is 2 pi over b, your frequency is b over 2 pi. Or I complete a cycle, I complete b number of cycles every 2 pi, or it takes me 2 pi to complete b cycles, right? Or this long to complete 1 cycle, I should say, sorry. So for our solution, okay, which if we go backwards a little bit, okay, so again, C1 and C2 are the amplitudes for the different cosine and sine functions, but we'll have to talk about that later because I can have 2 different values for C1 and C2. So is this my amplitude? Is this my amplitude? Is the sum of these my amplitude? Like, how does that work, right? We'll talk about that later, but what I can talk about is this value. Notice that this value in cosine and this value in the sine are the same. So the period, the periodicity, and the frequency are going to be easy to talk about. Okay, it's 2 pi over that value, and the frequency is the reciprocal of that. It is that omega, in this case, right, over 2 pi. Okay, so remember, omega is the square root of k over m. I'm, again, keeping everything in terms of k and m, spring constant and the mass. So if you haven't noticed, it's very important for us to find the spring constant and the mass in order to solve all of these things. Okay, so again, notice that the solutions, our solution equation has different amplitudes on each part of the solution. C1 and C2 can be different. So what we would do is we would change this to an easier form through the sine rule so that we can talk about a single amplitude which represents our system. Okay, so we would change this into a single sine function where a is the amplitude. We still have the same value here for the periodicity, and then we have this phi phase shift going on as well because we're combining different functions, right? So knowing this amplitude is important because it can tell us the extreme displacement, right? What is the highest or the lowest value that I will ever be away from my equilibrium point, right? And in order to figure that out, I need to know the amplitude. Okay, so let's talk about how to do this. So this is a very, very small formula that pops up in trig. Some instructors don't even talk about it, they just glaze over it, but it is important to talk about, so we'll talk about it now. This a value is basically coming from the Pythagorean theorem. It is the first coefficient squared plus the second coefficient squared and then square rooted. Okay, that should be very easy to remember. You're just using those coefficients from the sine and cosine functions that we have here, right? The C1 and C2 terms. Now, for phi, this angle phi, we can find it by using this equation. Okay, sine of phi is going to be C1 over this a value. Cosine of phi, the phase shift, is going to be C2 over this a value. Or we can use sine of phi over cosine of phi to find tangent of phi, which is just C1 over C2. So again, in order to actually find phi, you would find one of these values and then either inverse sine, cosine inverse, or tan inverse to find your phi value. Okay, and then you can plug it into this form. So some important things to remember is that weight is mass times gravity. Okay, and gravity is either 32 feet per second if you're talking about weight, or 9.8 meters per second squared if you're given a mass, right? So again, it's going to be very, very, very important here to make sure your units match up, okay? So if you're given something in pounds, you're not going to use 9.8 meters per second squared, right? You're going to use this one. The more common thing that will probably mess you up is you might get something in feet and then something in inches. You got to make sure everything is turned into feet in that case. Or maybe you're giving something in meters and then something in centimeters. You got to make sure everything is in meters, right? So make sure your units match up. That's probably going to be the number one thing to mess you up in this section, because everything else we're doing is pretty straightforward. Simple versions of the stuff we've been doing from chapter 4, right? It's just now that there's applications attached, but again, the math for it is pretty easy, okay? So just watch out for units and make sure that they are all the same. Okay, so let's go ahead and do our first example. All right, so looking at our first example, we have that a mass weighing 32 pounds stretches a spring 2 feet. Determine the amplitude and period of motion if the mass is initially released from a 1 foot point above the equilibrium position with an upward velocity of 2 feet per second. How many cycles will the mass have completed at the end of 4 pi seconds? Okay, so we have here that your weight is mass times gravity. All right, weight is mass times gravity, and we are given mass, right? So, or I'm sorry, we're given weight, so that's nice. I already know that 32 is m times g. G is the gravitational constant. I'm in pounds, so that means that I should be using 32 feet per second squared, right? So that will tell me what my mass is if I move some stuff around. So I get 32 over 32, my weight in pounds, over my gravitational constant. So I get a mass of 1. Okay. Here S equals 2. That is the stretching value. Okay, so I have my compressed string. I put this 32-pound weight on it, and it stretches it by 2 feet, right? So the stretching of the spring is 2 feet. We also have these initial conditions. So x of 0 equals -1 is because when I release my mass, right, I'm releasing it, the initial release, from a point 1 foot above the equilibrium position. So remember, equilibrium, positive direction, equilibrium, negative direction. So since I am above the equilibrium position, it is a -1 foot, right? Also, it says I'm releasing it with an upward velocity of 2 feet per second. So I'm moving it upwards when I let it go. So you can think about it as I have this mass and I'm kind of just, to be honest, throwing it upwards, right? So I'm throwing it up. So when it releases, it's already above and it's moving in a upward direction as I release it as well. And then it goes. It's not me pulling it up and then letting it go so it falls. I am throwing it upwards. I release it at a 1 foot position, but I'm giving it a velocity of 2 feet to start it off, right? So that's how we would interpret this. If I want to know how many cycles I'll be completed after 4 pi, I need to find the period first before I can do that. And in order to find the period, I need to find my equations of motion, or I can just find that square root k over m, right? That square root k over m is really what I need. So I don't have to go through everything, but obviously we will. And I'm also not going to derive everything. I'm just going to find the values I need, and I'll just go straight into my equation, okay? My solution equation, I should say. So here, mass times gravity is equal to the spring constant times my stretching factor, or my stretching value from putting on the mass. So remember, this comes from the equilibrium position. And so I can solve for k here. I know m because I just solved for it. I know the gravitational constant because I use that for, to find m. I know the spring value that was given to me, so now I need to find k. So if you notice, this mass times gravity is the same as my weight. So my k is actually w over s, okay? And my mass is actually w over g, so that's kind of nice, okay? So here's some equivalent forms of my equations I need. So the weight over the stretching value is 16. So I can throw everything into my solution right away, or I can throw everything into my x double prime plus k over m x equals 0 equation and solve from there. It doesn't matter. They're equivalent ways. They will get me to the same place. But I've already solved this in general, so let's just use our general equation because I've already solved all this, right? So again, C1 cosine t times the square root of k over m. So I can go straight here instead of going all the way to my, right. So instead of going here, I've already done the work in general. So I'm just going to use the general solution, right? I've already done the work for all of these cases, so I'm just going to use this instead, okay? It's up to you how you want to do that, but that's what we chose to do here, right? So this is my solution. Of course, this can be simplified. So C1 cosine 4t plus C2 sine of 4t. Now that I have this, I would need to use my initial conditions to find my constants. Okay, so in order to do that, obviously I'm going to need x prime. So now that I have x and x prime, I can use x of 0 equals -1. Plug that into here. So at 0, sign goes away. This turns into 1. So I got C1 is -1. So that's very easy. For the second for the derivative, the second one, my second condition, I'm going to plug in 0 here. So this is going to go away. This is going to go to 0, or I'm sorry, 1. So I'm going to have -2 is equal to 4c2, and that's very easy to solve for. I'm going to get -1/2 for c2, right? Now I have c1 and c2. It's asked me for a few things. One of those are the period of motion, but before we do that, I got c1, c2. Let's just write our answer here, right? So I just plug them back in. So now if I start to ask the questions that they want, one of them is the amplitude. I'll save that for later. We can find the motion, the period first. Notice that if I want to answer this last question, how many complete cycles will I have in 4 pi? I'm going to need the period for that, right? So my period is 2 pi over this value on the inside of my cosine, which is just pi over 2. If I want to know how many complete cycles I get in 4 pi, I just divide 4 pi by the period. It'll tell me how many periods happen in this time period, right? So I got 4 pi over 2, which will get me 8 cycles in 4 pi seconds, right? So now the last thing that I have is the amplitude. So we have a formula for that. Our formula for amplitude is this Pythagorean theorem for the coefficients we have. So in this case, that is going to be C1 is -1, C2 is -1/2. Oops, this should be a plus. Okay. And so when I add those together, I will get 5/4. Square root of 5/4 is, well, 1/2 times √5. Right. So that's our first example. So now let's get into the next section, which is free damped motion. So again, we're just adding a little bit of complexity here. So now my motion will be damped. This could be due to friction. If we're looking at the horizontal case, it could be friction along the rail that our mass is sliding. It could be friction within the spring. It could be air resistance. It could be whatever medium we're in. Maybe we're maybe our spring mass system is in I don't know, another sort of gaseous sort of medium, argon or something like that. Maybe it's in a fluid. Maybe there's a damping device applied. There's lots of things that can be happening here, right? So this is a more realistic motion though, because we know that as we have a mass on a spring in motion, it doesn't go on forever, right? If you've ever played with a spring or a slinky even, right, and you try to move things up and down, it doesn't go on forever, right? Things will stop and settle at some point in time. So here, this damping, we are going to assume is happening at a constant multiple of the velocity. Okay, so we're going to call it a damping constant, which is beta. It's very possible that this is not a constant and that it's actually a variable amount, right? Depending, maybe you're moving through different mediums, right? But for this case, we're going to keep it simple. We're going to say that it's a damping constant. It's beta, right? So it is a constant multiple of velocity, which means that it should be applied against an x prime term, and it is a damping value. It's slowing us down, which means it's moving against gravity. Okay, so it'll be subtracted, which means that when we move it to the other side of our equation, it'll be a positive value, right? Over here, it'd be negative, so we're moving over here, it'll be positive, okay? So this is our equation now, right? This should be very, very similar to you because, again, constant coefficients in a second order homogeneous equation. The way that we solve this is the way that we solve all of those equations by looking at auxiliary equations. Okay, so again, we're just applying the methods of section 4 to an application problem, right? This value here has a very common name, just like this is called omega squared. We generally refer to this as 2 lambda, okay? So we generally rename this as something else, and we rename this as something else, which makes it kind of helpful because now we have something that looks a little bit more similar to a perfect square, right? When we form an auxiliary equation, because we have a square over here, we have a 1 over here, and then we have a 2 times some other value over here. So it makes it easy to derive the math and the solutions. But again, we're just going to go through this process with the values that you're going to be given from your equation right away so that you can kind of jump straight to your answer instead of, you know, jumping through a few hoops. Okay, so let's form our auxiliary equation. Again, we're going to use r instead of m because, as you can see, there's an m everywhere here. So r squared plus beta over m times r plus k over m. So again, really all we need to do is throw this into the quadratic formula since it's a cubic, and we get something that looks like this. Okay, so to finish my derivation, I'm gonna kind of separate this into pieces. Basically what I mean by that is I'm going to split this 2 to go to this half and then to this half, so I can look at it as 2 different pieces. I'm going to do a little bit of algebra over here to make things nice. Basically what I'm going to do is I'm going to factor out a 4 to right here. So if I pull a 4 out from here, this turns into negative km, which is nice because that's a term we see here. This, if I pull out a 2, actually means that I have to divide by, if I pull out a 4, it means I have to have a 4 on the bottom. And then the square root of 4 is 2. So that when I multiply this in, it actually turns into a 4m, right? But inside of this, it'll be a 2m. So why am I pulling out a 4? Well, if I have something times something in a square root, and one of them is a perfect square, I can square root it. So I'm going to have square root of 4, which I can pull out, which will cancel with this because the square root of 4 is 2, which will give me nothing in front. So it makes it a little bit nicer, a little bit cleaner here, right? So now what I'm going to do is I'm really just going to analyze this discriminant just like we did in 4.2, 4.3 for our 3 different cases, which is in distinct roots, this turns into 0 and I have repeated roots, and when this is negative and I have imaginary roots. All right, so that gives me 3 cases, 3 different solutions. You already know what they're going to look like. We've done it lots of times. The difference now is that we're just going to apply those to our solutions to this, right? So we're just going to, I guess, cheat and just go straight to the solution so that when we solve these things, we don't have to form this from scratch every single time. We just find, once you have B, K, and M, we can just jump straight to the solution that applies, right, is what we're doing. Okay. So again, if you're having some problems with this part, from this step to this step, pull out a piece of paper, or hopefully you should already have paper and you should be writing this down as I go through it. But think about it, right? So think about this as a 4 over 4, right? If this was 4 over 4, it would really be 2 over 2, because when I square this, that'll give me a 4 beta squared and a 4m squared, right? So then when I put it in the 2, it turns into a 2 beta over 2m squared, and if I'm pulling out one of those 4's, that means that the 4 on the denominator has to stay there. Okay, so that's really what's going on here. I didn't really feel like writing all the math out. You've seen me do this in class a couple of times. It's just one of those tricks we can do to make things a little bit simpler to work with. Okay, so let's look at our different cases. Okay, case 1, we got distinct roots. Okay, the discriminant term is positive, right? The term in here is positive. If this is positive, I get this plus this, and this minus this. It's 2 real values. It also means that my system is overdamped, okay? Meaning that my oscillations are going to stop and go to 0 very, very fast. Okay, I'm overdamped. I'm kind of stopping my motion very quickly. This is very, very useful for when you have something like a building, right? So for instance, the buildings in San Francisco, they have dampeners on the struts so that the building doesn't shake a whole lot when earthquakes hit, right? So you want an overdamped system so you can stop the building from wiggling as quickly as possible, okay? So what does that look like? It looks like this crazy thing, okay? So again, C1, E to each of those solutions, right? So again, all I'm doing is I'm looking at the solution in its simplified form, right? R looks like this. So I have the C1 times E to the positive form plus C2 times E to the negative form. Remember, this whole solution is times T. This whole solution is times T. They're distinct. One's the 2 values added, one's the 2 values being subtracted. They're different values. You're used to this already. It just looks more complicated because we have extra variables in here. But again, it's just the regular quadratic formula answer. Okay. So what we're going to do is we're going to work on this a little bit just to make it a little bit easier to look at. Notice I have a common term. I have e to this plus this. So what we can do is we can separate that into multiplication of bases. Same thing here. Multiplication of bases, but I'm just thinking about it as one as negative. I did not feel like writing crazy fractions here. We'll just keep this as a negative exponent, okay? But notice what happens. This e to the negative beta over 2mt term is a common term, so I can pull it out, and then I have this left over on the inside, right? One is the positive form, the other is the negative form. So it's the discriminant portion of our solution under the square root. Okay, so that's what we get for case 1. For case 2, remember that's when this inside term is equal to 0. Okay, we call this critically damped, right? So what happens is that the discriminant portion goes away, and I'm left with just this negative beta over 2m. Remember, that's what happens when you have repeated roots. Okay, this is a double zero, meaning that this is a perfect square, so this shows up twice. Okay, remember what happens when something shows up twice? You have to keep them from being linearly dependent. So the second form you multiply by your variable before you throw that square root up there. Okay, so it's again the same thing from 4.2, 4.3 that we learned. It just looks a little different because we have all these extra things being applied. Okay, so this is what my solution looks like if I have basically a double root. Okay, now case 3 is your guys' favorite. It is when we have complex solutions. Oh, I guess I simplified this a little bit more. Again, I pulled out the common term so we can write it like that. Okay, case 3 is the inside term is negative, so I have a complex answer. We call this underdamped, okay, because we're going to have oscillations in our solution, cosine and sine. So the first form here, the negative beta over 2m, goes to the e, and the cosine part has the t times the discriminant portion. So notice I switched the order here, and that's because, again, if you come here, this is negative. So if I pull out the negative, then that's like factoring out a negative here. So the order switches. It just makes it positive. Okay, it's the same value. It's just not negative. Okay, you would have done it anyways. So this is the form of solution that we get when we have the complex solutions. So again, it's just a repeat of the things we've done already. It's just now we are applying them to this spring mass system. Right? So again, I have an alternative form for when I have the oscillatory form, the cosines and sines. Remember, C1 and C2 are going to be different most likely, so I can't really figure out what the actual amplitude is. So it's nice to be able to put it into a form where I can find the actual amplitude. So we call this entire term here the damped altitude. Not just the A is the amplitude, but this entire thing here, it's a function. It's our damping altitude function. We have it in this phase shift form. It looks very, very similar. We don't have to find this. This is already inherent. The phi we have to find. This is already here. This alpha we have to find. They're no longer called the period, but it's called the quasi period. Okay. So again, it's this portion. Let's come back here. It's this portion, right, under 2 pi, I'm sorry, for the period, and for the frequency, not frequency, quasi frequency, right? It's just the reciprocal of this, right? So let's do an example. So you might want to copy this down because I'm going to go to a new screen in order to finish solving it. It barely fits here, but we have a 4-foot spring that measures 8 feet after we put an 8-pound weight on it. So notice we're in feet and pounds, right? So we're using the measuring units. The medium through which the mass moves has a damping force that's numerically equivalent to square root of 2 times the instantaneous velocity. So what we want to do is we want to find the equation of motion if the mass is initially released from the equilibrium position with a downward velocity of 5 feet per second. So initial value here is at 0. We're stopping at the equilibrium position, but we're giving it a push downward, right? So find the time in which the mass attains its extreme displacement from the equilibrium position. What is the position of the mass at this instant? Okay, so go ahead and write all of this now, because again, when I go to the next page, we're gonna lose all this. We're not gonna be able to see it. So let's look and see what we have, right? So this 4 foot here doesn't mean anything. This is the compressed length. It doesn't matter to me right now. However, it does help me to figure out what the stretching factor is, right? What the stretch length is. So if it starts out at 4 and it ends at 8 after the weight, that means S is 4 feet, right? It's stretched 4 feet. That's why I used S for stretch. Get it? So S is 4. My mass is not 8, but the weight is 8. So we can use that to find the mass. We're in pounds, so we're going to use the gravitational constant of 32. I also have my beta value, right? Square root of 2 times the instantaneous velocity. And we have the info for my initial values. So x naught is 0. And my x naught prime is positive 5 because we're going downwards. So those are all the values that we have given to us. So again, I'm sure by this point you figured it out, but whenever we have a word problem, you really just need to write all the important information that's given to you and then figure out what to do with it afterwards, right? So maybe you write all the important info, read the question a couple times, and then you get started. But that's the info that we have. So let's go ahead and go through that problem. We know when we put the mass onto our 4 foot spring, it stretches it by another 4 feet. Okay. My weight is 8 pounds that I'm putting on the spring. My damping constant is square root of 2. My initial value is at 0, right? I'm releasing at the equilibrium point, and I'm giving it a force that gives it an initial velocity of 5 feet per second in the downward position as I go. So these are all the stuff that is given to me right away. So now I can use some of these to find what's missing. So what am I missing? Well, I'm going to need K, I'm going to need M, and that's pretty much it. M, K, beta, and S. If I have those things, I can have all of my solutions, right? So if we come back here, all of these, beta, M, K, right? Those are all the things I need. K, M, beta. Over here, M and beta, right? Over here, K, M, and beta. Those are the only things I need to find my solutions for any of these. So once I have those values, I can go straight to case 1, case 2, or case 3, or I can, once I have those values, just go ahead and plug it into my equation and then just solve my equation from scratch. Sorry, this would be my equation. That's fine too, right? Whatever you want to do. Again, as I said, I'm going to go kind of back and forth between those two methods throughout this video, okay? So I have my info, okay? My mass is going to be my weight over the gravitational constant, or 8 over 32, or 1/4, okay? K is mg. Mg is the same as weight. So K is W over S, or 8 over S, which is 4. So that'll be spring constant of 2. Note that if I wanted to start this from scratch, this is what my equation would be. Remember, beta over M, right? So beta is square root of 2. My M is 1/4. So square root of 2 over 1/4. You're going to divide by a fraction, so that flips over to this. Remember, this is omega squared. This was my 2 lambda, right? This is omega squared. Omega squared was K over M, or 2 over 1/4. So again, 2 over a fraction, so that flips up and turns into 8. Okay, so if you wanted to, you could just take this and then apply your quadratic formula, factor, whatever you want to do, and find your solutions. But we've already done that for pretty much every case. So now that I have M, K, and beta, those 3 values are the only things that I need. Okay. So real quick, I might want to check to know what situation I'm in. Am I case 1, case 2, or case 3? So I'm going to plug it in here. Note that I don't actually have to solve this all the way down. It'll be nice though, because I am going to use this value later, but I don't have to. I just need to know, is it positive, 0, or negative? Because positive, 0, or negative tells me if I'm overdamped, critically damped, or underdamped, right? That's all I need to know. What is this value? I don't need to know the actual value. I just need to know positive, negative, or zero. Okay, so I plug in my stuff. Okay, again, beta, m, and k are all I need. I plug all this stuff in. I get 8 minus 8, which is 0. Okay, so again, this turns into 1/2. So when I flip it over, I got 2 squared times the square root of 2. So 4 times 2 is going to be 8. Okay, and this is also going to be 8 because it's going to be 2 times 4. Or this value, right, we've actually already calculated k over m because I went ahead and found the equation right away. So it's 0. So I know that I'm in case 2. So my solution looks like this. Okay. Again, since I know what form it is, I can go straight to plugging things in. So what is this again? It's the roots here, or negative beta over 2m, right? That's what these things are. Again, just to go backwards, again, you should have this written down. The solutions are just negative beta over 2m. That's all that I need. I don't have to go through the whole process, but you're fine to do that, right? So just look at this, negative beta. Okay, that's where the root 2 goes, over 2m, so 2 times 1/4, that's really just this thing, okay, without the square. So then that will give me 2 root 2, and when I squared that, that's when I got the 8, but I got negative 2 root 2, okay. So this is my solution. Don't forget that constant to keep it linearly independent from each other because it's a repeated root because of case 2. So then now I can start to solve using these initial conditions. So I need the derivative. So x of 0 means that I got c1 plus nothing. This goes away, right? 0, 0 gives me c1 equals 0. Very nice. Okay. X prime of 0 equals 5. Okay. Well, this is 1. This goes to 0 because of the t. This goes to 1. So I got the negative 2 root 2 c1 plus c2 is 5. I know c1 is 0, so this goes away, which conveniently gives me c2 is 5. Okay, so that means my solution simplifies because this goes away because c1 is 0. So I got c2 t e to negative 2t root 2, but c2 is 5, so I got a very nice solution here, and that's my answer. Okay, now I'm not done because that's not everything they're asking for, right? So let's come back to the equation real quick. Find the time at which the mass attains its extreme displacement. So when is it the farthest away from the equilibrium point, and how far is that distance? That's what we want to know. So we found the equation of motion already. So now if I want to find the extreme displacement, okay, notice again, normally for extreme displacement, we would use a equals the square root of c1 squared, c2 squared, what have you. But that's for case 3. Okay, we're not in case 3. I don't have sine cosine. I'm not in this case. I can't find a here because I don't have case 3, right? Which is when I have a mixture of trig functions, of my periodic functions. I'm here. I have to optimize this solution, right? So, when am I the furthest away? Well, that's going to be when the first derivative is 0. Okay, that's when I have no velocity. Remember, at the top of a hump, right, I'm going from going up to going down. So there's a brief instantaneous motion where my velocity slows down and goes to 0 when it then changes direction, or vice versa from the bottom side, right? So my extreme displacement, my maximum away from the center, happens when the first derivative is equal to 0. So I'm going to take this first derivative for this one. Gotcha, right? And I'm going to set it equal to 0. So let's differentiate this. I can go here. Basically, all the terms I had c1 go away. This goes away. I'm basically going to have this, but instead of replace c2 with 5, right? Because c1 is 0. So I can use this, or I can do this all over again. It doesn't really matter, okay? But this is the value that I'm going to get, okay? c2 is 5. That turns into 10 root 2. This should be 5. When I did this, however, I did it straight from here. Okay, I didn't go up here, but it doesn't matter. It's the same thing. So setting this equal to 0 lets me try to solve. It's hard to solve this when it's just equal to 0. It's much easier if I factor out the e term, because e will never be 0, right? Which leaves me with this. So this is only going to be 0 if this is 0, right? So I set this equal to 0 and I solve for this, which is very easy to do. So I have that t is 5 over 10 root 2, or to simplify this, root 2 over 4, rationalizing the denominator and simplifying this term, which I can call 1/4 root x. I don't know where this x came from. I must have copied and pasted something incorrectly when I try to compile this from LaTeX, but this is just 1/4 root 2. Okay, I don't know what this x is for. I'll fix that in the write-up. Right, so when I simplify this, so this really should just be say equals to, not s and x. It should say this is equal to each other. I have no idea what happened here. So what that means then is that when I know what it's supposed to say. This is the seconds, and no, this is fine. Sorry, x is my function. Okay, it's tripped me out a little bit. This is my function. So when I plug this into my function, this is 1/4 square root 2. So plugging square root 2 over 4, or 1/4 root 2, into my position function will tell me how far away I am at this time. Sorry for the confusion, you guys. Okay, and that will be about 4.8 feet. Okay, so again, when I plug this in here, right, I plug this in. This is my equation. So 5 times 1/4 root 2 simplifies to 5/4, right? 5 over 4 times root 2, so 5/4 root 2, e to the negative 2t root 2. So when I plug in 1/4 root 2 here, the 2 root 2's turn into a 2, and 2 over 4 turns into a 1/2. So I basically have 2 over 2, which is 1, which is why I got the negative 1 here. Okay, so when I plug this value into my x function, that's what I'm doing here, right? This is not times something. This is the exact value I get out, and this is the approximate value. I think it was something like 4.801 something. That's unnecessary. 4.8 feet is fine. Okay, so let's move on to our next our next discussion, which is the last discussion that we have regarding the spring mass constant, and then we have one more thing to talk about. Okay, so let's go over the next section, which is driven motion. Okay, so what's happening here is that our function has something, our system, I should say, has something that is consistently adding in motion to the system. Okay, there's something driving our spring mass system at a constant, not a constant rate, but consistently adding energy into our system. Okay, basically this is what's happening when we have a non-homogeneous system, right? So we still have the same equation. So notice that for this equation, I have a damped system with what we like to call a forcing function. Okay, a forcing function. This adds in energy to the system to keep the mass spring system going, right? So I don't know, I guess you can think of a machine when it's turned on, that keeps the system running, right? If you were to just kind of put a spring mass into motion over time due to the damping of just regular physical world, right, it'll eventually go to 0. But this forcing function, basically whatever it is, this driving force, driven motion, will keep our system going as long as our machine is turned on, and as long as whatever it is that we're working with, we need it to work. Okay, so here again, f of t is our forcing function. what we did not show in our derivation, well, we did. We kind of showed that m times x double prime is acceleration. But what I did not talk about was dividing everything by m. But as you notice, everything here is pretty much divided by m, right? If I multiply everything by m, this is mass times acceleration. This is just the damping function. This is just the spring constant, right? So this f of t is basically our forcing function divided by the mass of the spring, okay? So really what that's doing is it's just allowing us to keep everything in standard form. Things are a lot easier in standard form, okay? But if we were to have everything multiplied by m, this would be acceleration, this would be the damping, this would be the spring constant, and this would be a standard f of t forcing function, okay? So when they give you this forcing function, what we're doing here, if we're using all the equations that we've done so far, we gotta remember to divide by m, or you just use the regular function and multiply your equation by m. So really the pieces are the acceleration due to gravity, m times acceleration, plus the damping portion, beta times x prime, the velocity, plus the spring constant, x times the position, will be the forcing function. So here really what we're doing, so we're just dividing everything by m. So use that as you will, but that's really the way that everything's been put together here. Okay, I just did not propose it to you in that manner, but that's really what's been going on. Okay, so the solutions to this non-homogeneous equation is made of what's called a transient solution and a steady state solution. So I've said this real briefly just now. I don't know if you caught it or not, but this forcing function is basically our steady state solution. Okay, so our solution is the general solution, which we'll call the transient solution or the complementary solution. So it's a transient solution, and the particular solution for this non-homogeneous case, that's our steady state solution, because it's constantly adding energy into our system to keep it going. Okay, so if we have motion that does not have a damping portion, that's going to change our equation a little bit. Basically, this just goes away, right? And the transient portion will also disappear. Basically, it just falls out when we solve for this solution. When I say falls out, it'll generally either C1 will, the coefficient that's attached to it will be 0, or it'll just kind of cancel out when we're adding or subtracting things together, right? So this is when I have a forcing function with dampening. If I have a forcing function with no dampenings, like our first example, okay, it'll look like this. It's basically just a non-homogeneous case, right? So what we should talk about is that when the right conditions are present, okay, especially in an undamped sort of situation, it can happen when we have a damped portion as well. If this is a small damping, if our forcing function overpowers our damping function, we can get what's called pure resonance. Okay, pure resonance is very important. It has many applications. Some are really cool, some are not. So we'll talk about that. Okay, so basically, if we have pure resonance, our system is going to oscillate back and forth until something breaks. Okay, either the spring is going to go past its elastic capacity and is going to break. If we're modeling a bridge, okay, there's something called the Tacoma Bridge. You can Google that. Maybe I'll put a link to that, but you can YouTube that. It's the Tacoma Bridge failure. Basically what happens is that the bridge started vibrating due to wind, and there is no dampeners in place, so it just kind of oscillated out of control until the bridge broke. Okay, that used to happen a lot with buildings as well. Very tall buildings. When the wind hits them, they'll vibrate and they'll start to sway, and they'll get into basically a pattern where the vibrations build off of each other and the foundation can't hold anymore, and it breaks. Okay, this happens if you've ever had what's called a speed wobble. if any of you guys skateboard or rollerblade or ride bicycles, sometimes your bicycle or your skateboard will wobble a lot. If it does it too much, you can break your axles, your ball bearings. If you've ever seen the videos where people put a speaker up to a glass, when I say a glass, I don't mean like a window, I mean like a glass cup, like a wine glass. If you hit it at the right frequency, what happens is that the glass vibrates until it shatters. It has pure resonance until it fails. Okay. There's been a lot of research lately about levitation from resonance. So if you, I don't know, I guess just Google that too, levitation, sound levitation. So there's some people, I think they're at MIT, they built a box that has speakers on all sides of the box, and basically what they're doing is, you know, they're able to control the frequency in a way that allows you to levitate a ping pong ball and then kind of move it left, right, up, down, side to side kind of deal. Okay, I'll try to look for those things and I'll add them to the links of, below this video. So this whole process is basically the frequencies of the waves that we're looking at, of the forcing function and the solutions are very, very close. And you basically get constructive wave interference, where one wave adds to another wave, or superposition of waves, and then you just get a very, very large amplitude until basically your system cannot handle it, right? And something fails, right? So let's look at an example. So we have a mass of one slug, which is attached to a spring, stretches it to 2 feet, and then comes to rest in the equilibrium position. Starting at t equals 0, an external force of f of t equals 8 sine 4t is applied to the system. We want to find the equation of motion if the surrounding medium offers a damping force that is numerically equivalent to 8 times the instantaneous velocity. Right? So this is the example that contains one slug. Again, I have never heard of a slug, but when you Google it, it is basically 32 foot-pounds of force. Okay, so it's a force sort of unit, and it uses the gravitational constant of 32 feet per second. Okay, so it's basically one of these times 32, right? So that's nice because we can consider the mass as 1. It is a mass, right? It is a mass, not a weight. It's a mass, so the mass is 1. The gravitational constant is 32. And then everything else is in feet as well. So we're already in the units that we need to work on. So let's go ahead and write the things that we have, which is mass is 1 slug. My stretching value is 2 feet once this slug is applied. So a slug is roughly equivalent to 32 pounds, but one slug is a mass of 32 pounds is the weight of it, right? So 1 times the gravitational constant, mass times gravity, gives us its weight. So it's nice that we can just use it as 1 mass, right? So here my gravitational, my damping constant is 8. And my function, since everything else is divided by m, right? It's 1 over m, but m is 1 of my function. So this shouldn't have been a positive here. It's 8 sine of 4t. So it basically just turns into 1 over 1 times my function, which is just my regular function. Okay, now if this was a mass of 2 slugs, this would be 4 sine 4t. But we have a nice value here. Okay. My constant k is the mass times gravity. So mass is 1, gravitational constant is 6, my slug is 2. So I throw that all in and I get 16. Okay, my initial value of 0 says that I am applying this external force at the equilibrium position. So x of 0 is 0. Okay, that's my initial point. The derivative, the initial velocity, okay, happens at 0. which is 8 sine of 0. So again, I'm not moving it already when I start going. I'm just starting it from equilibrium, and then I'm kind of just turning my system on, right? So if I wanted to put this all into an equation, remember this is beta over 2. I'm sorry, not beta over 2, beta over m. M is 1, so that's just 8. This is k over m. K is 16, m is just 1. This is my function divided by m. Again, m is just 1. Okay. So this is very nice. I have a very standard non-homogeneous equation that I can solve. If you notice, so again, I said I'm going to go back and forth in the way that I'm solving. So I have k, m, and beta. I can jump straight into my solutions if I wanted to. But notice that this is actually really easy to solve, right? So the auxiliary equation looks like this. So I know what the solutions are. It's a double root. So I just apply the double root, okay? Very straightforward. Or I could have just, checked the, that beta over 2m squared minus km, basically this, right? B squared minus 4ac, and just check and see what happened there, okay? So this is my general solution. To find my particular solution for the non-homogeneous case, I can use undetermined coefficients. I could also use variation of parameters. We have different, a few different methods. In fact, if I wanted to, I could have used the annihilation method straight from the beginning and done d plus 4 squared plus whatever would have annihilated this. If I had wanted to, it's all the same thing. Again, it's just all the methods we've been learning already, right? So my particular solution will have this form. Again, I'm not using the annihilator method. I'm using the superposition method. So some constant times sine of the 4t. So my general solution, my particular solution will look something like this. Okay, I need to solve for C3 and C4. So I'm just going to take a few derivatives and I'm going to plug it into this equation. So again, when you have the non-homogeneous case, it's nice to have that equation you're working with, especially if you do undetermined coefficients. If not, I could just take these solutions and then use the variation of parameters form. I started to do that on my own and it just wasn't very nice. It turned out to be a lot of work because you're mixing these solutions. The Wronskian is easy, but then when you mix these with the Wronskian with the sign that you have here for the forcing function, it doesn't integrate very nicely. It's a lot of integration by parts, and a messy integration by parts at that. So I decided that indeterminate coefficients was way easier to do because the derivatives are very simple. Okay, so again, you really want to choose your method based on whatever is easiest, right? So variation of parameters was easy. The first and second derivative are very straightforward, right? So you're just doing the chain rule a couple of times. There's no product rule, so it doesn't keep getting longer and longer. You just kind of keep adding this 4t and changing your trig functions, okay? So throwing these into our equation here and then equating the result with this forcing function gives me the following, okay? So I'm going to throw in my x double prime. Again, the x double prime is 16s, x prime is 4s, and this is just the regular coefficients. So throwing it in here, I'm going to add 8 times the first derivative. So again, I had some 4s here, so I'm going to end up with some 32s. Same signs though, however, and then I'm going to add 16 times the regular coefficients. And so notice that quite a few things cancel. This term and that term will cancel. This term and that term is going to cancel. And so really I'm just left with this middle part here. Okay, I would have put all of this on one line, but it doesn't fit on one line. For this form, maybe in the write-up it does. But this is what we'll be left with. Okay, just that middle part. Right. Equating that to the forcing function allows me to figure out what my coefficients are. right? So obviously there's no cosine here, so this part goes away. Equating these two, tell me that negative 32C3 is equal to 8. Again, the C4 goes to 0. And then I get this equation, so when I divide both sides, I get a negative 1/4. Okay, so that tells me that I have this form now for my solution. So now I need to use the initial conditions to solve for C1 and C2. So going backwards real quick, these are my initial conditions. X of 0 is 0, x prime of 0 is 0. Okay. Oops, too far. So I have my regular solution. I'm going to need x prime in order to use that initial condition. So I should just do it now. Okay, so I get this. So this is from here. This is the product rule. So I get 2 terms from this one. And then this is the chain rule from this derivative. Okay. X of 0 equals 0. So into here, I'm throwing in 0. So this is C1. This goes away. And this turns into a 1. So it's a negative 1/4. C1 is minus 1/4. That's a nice, easy answer. My other condition was that x prime of 0 is 0. Because remember, I started at equilibrium and then I just kind of let it do its thing. I did not start it off with an initial velocity. The initial velocity came from the forcing function itself. So if I plug in 0 here to this long thing, this goes away, this turns into C2, this goes away, and this is negative 4C1. So I got negative 4C1 plus C2 is 0. I already know what C1 is. This is 1/4. So this is a negative 1. So C2 is 1. Okay, I throw those values, C1 and C2 in, and this is my solution. All right, so let's look at our last section, which is the analog of the series circuit. So we're going to apply all of the methods we've just been talking about to our circuits. Okay, so let's look at the basic circuit, the one that has a little bit of everything. So one capacitor, one resistor, and one inductor. Okay, we call this the LRC circuit. Okay, just has a little bit of everything. So again, this is the energy source, right? This is what supplies the voltage. The voltage and the amperage and the current are all related, and they go through the system when it's closed. Okay, if it's open, there's no voltage, there's no amperage, there's no inductance going on. Okay, so our equation around this circuit, so I'm changing the notation a little bit. Again, I told you I don't really like the Leibniz notation, so we're going to stick to this prime notation. So it's L times the derivative of I plus R times I plus 1 over the capacitance times the charge. Okay, so again, resistors are in ohms, capacitance is in farads, the inductance is in amperage, I believe. Okay, and the energy that's going through the system is volts, right? That's the voltage across, and we're looking for basically the charge drop across the system, right? Q is our charge, right? So what we want is our variable here is Q, right? What we're basically trying to solve is Q. So let's kind of change everything into terms of Q. I is the same as Q prime, right? So this will turn into Q prime, the derivative of Q. I prime is the second derivative of Q. So we can substitute all of that into our system. And now we have a second order dE. Okay, everything in terms of the charge function, right? So let's talk about the system a little bit. When E of t is 0, we say that the electrical vibrations of the circuit are free, right? If E of t is not 0, then the vibrations are forced. Okay, we have no energy coming into the system. Here we do have energy coming into the system, right? If there is no resistance, then Q of G of t, or basically the solution to the general equation, or the Q of C. If you want to think about how the book talks about it, the complementary solution, that's our transient solution, right? This is our general solution to the homogeneous case. If EFT is periodic, then we're going to have a steady state or forced solution, okay? So let's look at our second order DE, and let's look at the auxiliary equation. Again, we'll use, we can use R here. I'm sorry, we can use M here because M doesn't pop up for series circuits. So this is our auxiliary equation. It's second degree. We solve it like anything. We use the quadratic formula, right? So this is what my solutions are going to look like. So I have different things that happen pertaining to the discriminant here. So if this is positive, just like before, this will give me an overdamped system. If it's 0, give me a double root. It's critically damped. And if it's an imaginary complex solution, it's an underdamped system. Okay, so very, very similar to what we were doing for the last example, right? Again, because these are similar models, but for different things, right? So again, notice that I'm going to have a common factor of e to the negative 2RL here for all of these cases. If this is positive, I got this showing up twice. If this is 0, it's a double root, it's still there twice. If this is complex, it shows up in the sine and cosine portions. Okay, we saw that last time. I'll always have this as a common factor, right? So let's get started with an example. Okay, again, we're just going to build this equation and solve it. So here I'm giving you all of the things that you need. We have an LRC circuit. L is 1/2. R is 10 ohms. The capacitance is 0.01 farads. I have a forcing function. I have 150 volts being supplied to my circuit, and the initial charge is 1 capacitance, right? And the initial current is 0 amperage. Right, so we have these things. We want to know what is the charge on the capacitor after a long time. So after we get our solution, we're basically going to take a limit, right? Now, first thing we want to do is let's change this into Q. Okay, again, notice everything I do really relies on Q. So let's change I into its analogous Q form, just Q prime. So I of 0 means Q prime of 0 is 0. Right, so that's my initial condition for this, and then this is my initial condition for the charge. Okay, our equation becomes this: L is 1/2, I, or Q prime, is 10, right, 10 ohms, and then for the capacitance I have this, and this is my forcing function. I am connected to a 150 volt system. So let's change this so it looks a little more normal. Right, it's 1/1/100ths, or 100, right? So this is the equation I want to solve. I can come straight here and look and see if I'm overdamped, critically damped, or overdamped, right? What kind of system I have, or I can just take this and plug it in to the full quadratic formula. It doesn't really matter. You can do whatever you want. It's all the same thing, right? So here we're just going to check. Again, if I check, I don't have to actually calculate the value, but I have 100 minus something more than 100. So I'm going to be in case 3, right? Case 3 is the underdamped case, right? Negative, I'm going to have a complex solution. Sorry, let's come back here. Right, so then my solution will look something like this. Okay, so if you notice for this first part, I'm not actually calculating anything. I just plugged everything in. This is easy to calculate. For this one, I calculated it over here because it's very easy. This is 200 minus 100, which is the square root of 100, which is just 10, right? So here I'm just showing you, I'm just plugging it in. It didn't make sense to plug it in twice. It's very easy to calculate. If it was not, I would have just plugged in the same thing. So just to keep it simple, this is what our answer looks like, right? 100t, or sorry, 10t on the inside, and a negative t to the exponential portion, okay? So I need to use my initial conditions to figure things out. Maybe before I do that, I find my particular solution, because this is a non-homogeneous case. So the particular solution is equal to a, because it's just a constant, right? It's 150. And so the derivative of a constant is 0. So when I plug that into here, this is obviously 0 if the first derivative is 0 plus 100. So I really have, this is what I get out, right? 100 times a. I know that that's equal to 150 because that's my f of t, right? That's my e of t function. So then a is just 150 over 100, or 3/2. Okay, very, very easy. So that's from undetermined coefficients. This is not that square root stuff that we're doing with C1 and C2. This is just the form of my particular solution here. Okay. Now that I have this, I can write down what my full solution looks like in general. Okay, it looks something like this: 3/2, and then my homogeneous general solution is here, plus the particular solution. So now I need to find C1 and C2. So I use those initial conditions. In order to do that, I need the first derivative, because I have an initial condition for the first derivative. Okay, so let's find that. And then I have Q of 0 is 1 capacitance. So let's look at that. Okay. Q prime of t is going to be a very long thing, so I had to write it on 2 lines. So this gives me 2 functions, the first 2. Okay. This is the product rule also, so it gives me the other 2 answers that have C2. I have this 10 on the inside, so when I do the product, the chain rule with the product rule, it has to come outside and multiply, and this part goes to 0. So this is what the first derivative looks like, right? As I apply my initial condition to the charge function, I know that this is going to equal 1. So plug in 0, this goes to 1, this goes to 1, I got C1. Okay, this makes this whole thing 0, and this is 3/2. So I basically have C1 plus 3/2 equals 1. Okay, so that gives me C1 is -1/2 when I subtract this to both sides. For the next one, I need to plug in 0 into Q prime of t, or the current function, right? The function that gives me the current, I. So when I plug this in, all the sign pieces go away. So I got a -10. This whole thing just turns to 1. So -10C1 plus 10C2, because this goes away, right? Which means that these things are basically equal to each other, right? So when I move this over, the 10s will cancel. I get C1 equals C2. So I got another -1/2, right? So this is what my solution then looks like. -1/2, -1/2 are the coefficients. And I can pull this out as a common factor, as I said before, right? We've seen this before, but sometimes we pull it out, sometimes we don't. It doesn't really matter. It's really up to you if you want to or not. It's just a style thing. How do you want it to look? This is fine as an answer. You can pull it out and make it a little bit cleaner, right? Which is a little nicer. And that is our answer. But we're not done, because the question was saying, what is the long-term charge over the capacitor, right? So again, this is the charge. So what's the long-term charge? Well, it's going to be the limit of my function as time goes on to infinity. If you don't know about capacitors, they basically they kind of disperse their charge intermittently. It's like on and off, on and off. That's not really how it works, but that's kind of how it works. So long term, this is going to go to 3/2. I have an oscillating function here, and I have a negative exponential. This dominates this function when you're talking about a limit. This decreases way faster than this thing oscillates. If you're not happy with that as an answer, you can apply L'Hopital's rule here and kind of just differentiate it and see what happens there. But it should be pretty clear that this goes to 0, which leaves you with this constant value. And that is our answer. Before we're done, you do have a classwork. I'll put the due date up as I update your video now. Sorry it took so long to make this. It's obviously a lot longer than our regular videos. Hopefully we don't have too many that are this long again. So here is your classwork problem. Okay, so I'll leave this here for a second, although you can 100% pause it so you can write it down before I'm done talking. But let's go ahead and solve this. Try to simplify it as much as possible. Show all your work, and I'll write the solutions to this, and I'll post them for the due date. Thanks.